Hello, everyone. Welcome to CSE365. We are now 2 modules into this course. We're starting the 3rd module. How did everyone feel about the assembly crash course module? Is it worse, better, shaky? I'm seeing some shaky. Did anyone like the module? Does anyone feel like they learned something from the 2nd module? Maybe what you learned is useless or something, but did you at least learn something? All right, well, hopefully it'll end up being useful. That's a good start. So if you didn't like the 2nd module, sorry, the 3rd module is modules 1 plus 2 combined. So as I said on Tuesday, Talking Web was you are an HTTP client. Module 2, as you're very familiar now, write a bunch of assembly. Module 3, you are now the web server. So we're going to be writing assembly code to parse HTTP requests and return adequate responses. I don't know what last semester would say, but I think this module is actually easier than the 2nd one. There's not a whole lot of logic. I mean, you're going to have to implement some very, very, very basic parsing, but it's like find a space and replace the space with a null byte level of parsing. So it's not too crazy. Yeah, so that is the module we are now on. It is due in 11 days, 11 hours and 54 minutes. As always, start early. If you found yourself like starting yesterday on the module and then you're like, what the heck is going on? None of this makes sense. Really wish I could have attended recitation for the last 2 weeks. I encourage you to start early. Okay. So in this module, we are primarily shifting our focus from just writing x86-64 assembly to doing that in the context of Linux, where we have access to the Linux kernel and are making system calls. So Linux is our environment in this case. So if we want to interact with our environment, do something less lame than just put a value in RAX, like open a file or like write to the screen or something. This is where Linux comes in. Linux is our abstraction layer. Our operating system is our abstraction layer that represents our environment and allows us to perform different tasks. Okay, so I think on Tuesday, we demonstrated this. So what the heck is this? Well, this program right here makes 3 system calls. 3 system calls. They're all separated by nice little spaces. This very last system call is a refresher. If you didn't pay attention on Tuesday, didn't watch Tuesday, we'll do a quick recap. This last system call is probably the simplest of the 3 system calls. As you see, all system calls end with a syscall. I mean, technically this a little bit more, but they really just end with system call. Syscall is the name of the instruction. And you specify what system call you're going to make. There's like 300 system calls to pick from. You specify which system call you want to make by putting a number in RAX. And that number in RAX now means this is the system call I want to make. And why put it in RAX? Well, this is not the CPU's decision. This is Linux's decision. It's a standard. We're learning about lots of standards. HTTP is a standard. Calling conventions are standards. Well, it turns out that the Linux calling convention also follows a standard. It's not, I mean, maybe you can consider it arbitrary, but it is what it is. So you select your system call and put it into RAX. So we're saying right now, make system call number 60. Similar to when we went over call, the first argument to a function, and you could almost treat a system call as a function. It's a little bit of a special function, but you could kind of treat it as a function. The first argument to this function goes in RDI, because that is what the standard says. Put the first argument in RDI. So 60 is exit. How do we know that 60 is exit? Well, basically just look at documentation, and this is a very simplified version of that documentation. It's x64.syscall.sh. I think there should be, there's not a link. We'll add a link to that to make sure it's very accessible, because this is very useful. And this, whatever this resource is, I actually don't know who the heck put this together, but someone put it together and it's correct. And they say that system call number 60 is exit. So we've got the exit system call. It takes one argument, and the arguments, they're calling it error code. It's also like the return value, it's some number that when your process exits, it returns that. So almost like in the same way that a function can return some value through RAX, a process itself can return some number through this exit code. So we are specifying 60 0 syscall. So this is semantically equivalent to exit 0, if you've ever written something like that in C. Of course, if you'd put 42 here, that would be semantically equivalent to exit 42. Okay, so that's probably the simplest system call that we're looking at. The next system call we'll look at is this first one. So we are making system call number 2. Why number 2? Because 2 went into RAX, and that's what the value of RAX is when we make the system call instruction. System call number 2 is open. So you could probably guess what the heck that means. It means open, and the first argument really gives it away, open a file. So we're able to open some file using system call number 2. It takes 3 arguments. It takes a file name, which is like the path. So for example, if you wanted to open /flag, you would put /flag as the file name. And recognize here that this is a pointer. So /flag, the bytes of that would be located somewhere in memory, terminated by a null byte. And then we specify our flags. So our flags let us determine, are we opening this file for reading? Are we opening this file for writing? Are we opening this file for reading and writing? And there's other options also, but those are kind of the most crucial ones. You didn't really care. You could just like always open your files for reading and writing and never think about it. But that's not necessarily a good idea. If you're only going to read it, it's just clearer to say that I'm opening it for reading. And then something weird happens later and someone's accidentally writing to this thing, it just fails, and it's nice that it fails and yells at you. And then we have this mode thing. So one of the options in this flag is the ability to create a file if it doesn't exist. This mode thing specifies the permissions of that file if you end up creating it because it didn't exist. So that is what's going on here. How do I know this, right? I'm just kind of like speaking from memory right now. Well, the best way to find out that everything I just said is true is to do man space 2. So this is selecting man page number 2, open. And this right here will give you a whole bunch of nice information. It's like technical, but it's not that bad, right? It says like the open system call opens the file specified by path name. If the specified file does not exist, it may optionally, if ocreate is specified in flags, be created by open, right? Everything I just said is in this man page. So if you're wondering what the heck a system call does, read the man page for that system call. And there's a good technical, but not like unapproachable piece of text that's going to describe what's going on. Cool. So one of the important things about this system call is it returns something. So I think if I search for return results, where is it called? Return value. So similar to how a function returns something in the RAX register, because by standard we put something in RAX and that means that's the return value. Linux system calls do the same thing. So RAX kind of has two meanings with a syscall. RAX is simultaneously your system call selector before you make the syscall, and also the return value of your system call after. So RAX kind of gets used for both, but one's before, one's after. So RAX will contain the result value. Of course, back in the world of exit, this exit system call, there's nothing goes in RAX because your process is dead after you make this system call. So there's nothing that's going to happen after this. So this open system call returns this thing called a file descriptor. So open, return the new file descriptor, or -1 if an error occurred, in which case error no is set appropriately. So a file descriptor is a number, right? Everything that ends up in a register is a number. Now, some of these numbers mean different things, right? You could have a number that truly is just like an integer value, like that's how you're kind of perceiving it. You could have a number that is an address, right? It's a pointer to somewhere in memory. In this case, it's kind of a different classification of number. It is a file descriptor. So a file descriptor is going to be something literally like 0 or 1 or 2 or 3, and it'll just count up. Normally, you can have up to 256 file descriptors. I don't know, maybe that's configurable. Doesn't really matter. But this file descriptor is how you can refer to this file in the future. So you've opened it. Your process within the Linux kernel now knows this file is open, and it has associated that open file with a number. And then when we want to do something else like read or write, so as you can see here, we've got read system calls and write system calls. They take file descriptors. So you can read from that returned value when you open. You can read from a file descriptor. You can write to a file descriptor. Maybe you're thinking, why not just pass the file name to this thing also and pass the file name to this thing also and just always pass file names? Why are we doing this like layer of indirection through file descriptors? It turns out it's very nice. First issue or first reason is that your file, once it's been opened, has some amount of state. So if I open the /flag file and I read 1 byte from that file, I'm going to read the first byte of that file. If I go on to read a second byte, or I read 1 byte again, I'm going to now get the second byte of that file. And if I do it again, I'll get the third byte of that file. So there's a state associated with it. So we can't just reference things by some path. We need this like state encapsulated thing. And we represent that from user space, from our program as a file descriptor. The kernel knows how to find the state given a file descriptor. Okay, so that's why we have file descriptors. And so what's going on here is we open, so we're specifying open. We're specifying our second argument, or our first argument, the file name. So that's offset path. So offset path is here. We are opening hello.txt. We are specifying flags of 66. This seems incredibly convoluted. What the heck is 66? Right? Where are all these magic numbers coming from? So 66 is the underlying meaning of 66 is this like bit field thing. So if I represent this as binary, so 66, you will see that we have 2 bits on. We've got this bit on, we've got this bit on. Each bit means a different thing. So we have the 2 value on and we have the 64 value on, right? It's 64 plus 2 is 66. Those are all both powers of 2. So we need to figure out, if we want to know what this is what the heck is 64 and what the heck is 2? Because that's really what 66 is. It's the ORing of 64 and of 2. So 2, it's kind of, I've never thought about going backwards. I've never thought about starting with the number and then trying to resolve what the flags are. That's a little bit trickier, I guess. We'll start instead with, I know what they are, and I'll show you how we know that that's the definition, because that's the more reasonable way of doing this. You don't normally start with a number and then figure out what does that mean. So if we want to open a file for reading and writing, so I said that's one of the options. You can open it for reading, you can open it for writing, you can open it for read-write. These things end up in the flags. So we have O read only, O write only, O read write. Additionally, we have all these other things like O create. We'll kind of ignore these other ones. O create means create the file if it doesn't exist. So these are the interesting values we're concerned with. And so I'm pretty sure we are specifying right now O read write. Here's the simplest way I know of finding the value of this thing. Inside of the file, or inside of this directory user include, we have a whole bunch of .h files. These are the same .h files you're used to when you write a C program and you include some .h file. These .h files specify the definition. One of these .h files specifies the definition of O underscore read write. I like just grepping through, so searching through this entire directory and looking for who the heck says O read write. If I do this, we'll see there are 4 places in the entire user include directory that have O read write mentioned. You'll also see that at least one of them has pound define in front of it. So really what I like to search for is pound define for whatever constant. We will see that O read write is 2. So of our 66, which is 2 or 64, This is what the two part is. It means open it for reading and writing. The other one is create. I just know that that's true because I wrote 66 on Tuesday. And this right here is, so this is right here. If we look at this value, it's surprising. This is represented as octal right now. Why octal? I don't know. They like representing this number as octal. I know it's octal because in C, if you start a number, or at least I'm highly confident, you start a number with a 0, it's octal. In Python, to do that same sort of thing, you start it with 0, 0, similar to like 0x. This thing, which is octal 100, is decimal 64. So we have 64, we have 2, we OR them together, we get 66. Alternatively, another way we could know that using Python actually is we could look at read write, and we could do create. And the OS module also has these things defined. So create ORed with read write says this thing is 66. That's how you do it. You OR them together because it is a bit field. Okay, so that means we are going to open this path, hello.txt, in read write, and then also create it if it doesn't exist. This is where the third argument comes in. If you decide to specify create, you have to specify with what permissions. And this is also a number that is very convenient to represent in octal, because each octal, not digit, each octal character, symbol, I don't know what the correct terminology would be there, but each one of these octal symbols, right, from 0 through 7, represents a different thing. So this, and we'll talk about this in a later module, access control. We're really not getting into permissions right now, but since we're doing it, we'll brief primer. This represents, okay, so I'm some user right now. If I am the owner of the file, what should I be able to do? Should I be able to read this thing, write this thing, execute this thing? For means read this thing. Then it's group, then it's other. So owner, group, other, and we're specifying read, read, read. We'll see, for example, actually, we can show this real quick. Live, cd, assembly. We've already previously created this thing. You'll see that it is read, read, read. If I chmod hello.txt to 444, backwards, we will see that this thing is read, read, read. If instead I do 777, this means everyone can read, write, execute this thing. If I do like 700, it means the owner can read, write, execute this thing, and no one else can. If you look at the flag, this is how the flag works. Only the owner, which is root, can read this thing. Okay, so there's our very brief primer on that. Doesn't really matter too much for us right now, but that's what's going on there. Then we make a system call, and that opens the file and creates it if it does not already exist. The file descriptor ends up in RAX, so the result ends up in RAX. We decide we want to save that off to RDI, and we'll see why in a second, if what's going on there. And then we get ready to make another system call. So this system call is system call number 1. What is system call number 1? Again, look at the documentation. It is the write system call. It takes 3 arguments: file descriptor, pointer to a buffer, and number of bytes. So this is going to be, what do we want to write to, what do we want to write, and how many bytes do we want to write? So what do we want to write is specified by a pointer. It's a location in memory, and then how many bytes to write from there, that's the count. So we specify the write system call. We specify that the thing we want to write is whatever the heck is at offset hello. So this is RSI. This is our second argument. We're starting right away with our second argument. You can do this in whatever order you want. We're saying offset hello, which is hello, comma, space, world, exclamation point, new line. We're saying that we want to write 14 bytes. Turns out this thing is 14 bytes. So we hard-coded it. It's 14. Remember when we wrote the stir-length function? This is where your stir-length function, if you wanted to not have to manually figure out this value, you'd call stir-length and then put stir-length's result in here. Instead, we did this by hand, though. And then we make a system call. So we kind of didn't, in this block, specify the first argument. The first argument, though, came in through up here when we saved off the file descriptor. We put that into RDI. And now that's the file we're referring to, is the result of this open system call becomes our first parameter to our next system call. So it makes sense in a lot of contexts to chain the result of one system call and pass that in as an argument for another system call, especially for this pairing of open system call, write system call. You open something and then you write to it. It makes sense that you chain these kind of together like this. So if we make this, so make test, we assemble it, we link it, we look at the underlying code. We'll see we've got all this nice code. Our offset things got resolved for us. So this is pointing at 4.8, which is our path. This is pointing at 5.2, which is hello. And we're making our 3 system calls. If I'm going to remove hello.txt, so hello.txt does not exist, and I run test, suddenly hello.txt does exist, and the contents of it, you can already see, is 14 bytes. And it says hello, comma, space, world, exclamation point. If I want to see all of that in action, so it's kind of maybe scary, like how do I debug this? What if something just went wrong? strace is a very valuable tool. On module 3, strace will be your best friend. In fact, on module 3, we automatically strace your program for you. There might be a certain context where you want to do it yourself. But the way that we confirm in module 3 that you're making the right system calls is we strace your program and we display those results to you. And that's good for debugging, and also that's how we check that you're doing the right things. So if I run strace./test, we see we have 3 system calls. We have the open system call, the write system call, the exit system call. You might say we also have the exec_ve system call. So we haven't talked about exec_ve yet, but if you want to start up some program, that is a system call. And that is the exec_ve system call. Technically, test didn't do the exec_ve system call. Technically, bash did the exec_ve system call, but strace likes to show it to us here. Maybe it's like right on the boundary, who made the call, because it's right when it's spawning. And then it also says the exit code right here. So we can see very, very nicely, it's like we're reading C, what the heck happened system call-wise. Well, we opened hello.txt, we opened it read, write, create. We did a mode of 444. Looks like, this is not good. Looks like we got permission denied. So how the heck did this work? That's interesting. Permission denied. And then you'll see that it said write -13. If you're ever writing to a negative value, that's bad. You're going to see it says bad file descriptor. I'm guessing what happened is this only works if hello.txt isn't. Oh. Well, okay, so here I'll show you what happened. So this works if we do it without the file existing. If we delete the file and then run it, we'll see open succeeds. We got 3 back. So 3 is just a number that references this file descriptor. It is this file descriptor. It references the open hello.txt state. This is all represented in the kernel. You specify 3, the kernel knows how to resolve that for when you do something like write. I think what happened here is if we strace it again, we'll see it fails. Does anyone know why this failed? Does anyone have a good idea of why this failed? Yeah. So it's not that it's trying to overwrite the file because the file already exists. So if we read the man page for man to open, it's a good theory. Like you could definitely imagine that being what happens. If we look at create, it says that if path name does not exist, create it as a regular file. I guess does it say what happens if it does exist? Maybe it doesn't say that. If path name, I'm pretty sure that if it does exist, it's like a no-op. It just doesn't do anything. The reason it failed here is that we're opening this file for reading and writing. What are the current permissions on flag or on hello.txt? It's read only. We created this file read only, which worked in the first case because when you're creating it, the permissions aren't necessarily respected because it's getting created and opened at the same time. But the second time we're going and we're trying to open it for read write, but we do not have permission to write to this thing, which is like, maybe you think that's lame. We created this file. What do you mean we don't have permission? Well, since we're the owner of the file, we can change the permissions on this file and give ourselves the ability to write. And now it says read, write, execute, read, write, execute, read, write, execute. We just gave all permissions for everyone to this thing. And now if we run this program again, we'll see that it succeeds. If we wanted to like make this more correct, probably what we would do is like 644, which means I can read and write this thing, and then everyone else can just read this thing, if that's what I wanted to mean. Clearly, since we're writing to this thing, it makes sense that we want the permissions of this thing to also be writable too. I know it's weird, like how did it succeed the first time? It's just when you're creating the file, like permissions aren't followed because while it's being created. That's just how Linux decided to implement things. You could definitely imagine that doing this when the file doesn't exist would result in an error because you don't have permissions, but that's not how it is implemented. Okay, so now if I rm hello.txt, and then I strace this, we will see now, well, we forgot to make test, and then rm hello.txt, yes, strace. We will see now we're doing 644. If I run it again, it succeeds. Why does it succeed? Because now we are able to read and write to this thing. So I keep typing like rm hello.txt. You could imagine that we don't just want to use the existing file if it already exists, but instead we want to recreate it from scratch, which totally could be a valid thing. So if we wanted to delete this file, guess what? That's a system call as well. So I believe it is the unlink system call. Unlink takes one argument. It takes a path name, and it just deletes the file. So unlink will delete our file. So if we want to do that, it's system call number 87. So let's go ahead and do that. Just to remind ourselves, move rex 87, yep. And then move RDI offset path and syscall. So if we want to delete the file before we create it, so basically this is like guaranteed we're in the creation pathway, and we make test and we strace /test, we will see, well, it says no such file or directory. I'm guessing, yeah, it's because we already deleted it. So it says like you're trying to unlink this thing doesn't exist, what the heck? You'll notice that this does not crash your program. When you miscall a system call, your program's not going to crash. The kernel is just going to yell at you by giving you a negative result in RAX that says some sort of meaning. That's fine. We then go on to create it and everything works. We could run this again. Now it works because the file exists, and now every time we run it, it works. If we preemptively delete it, it still works. It's just that first system call fails. So, I mean, if we wanted to, there is a system call called stat, and stat would allow us to detect what the heck is going on with this current path, and we could like check. I don't know. Probably you're going to get an error code here. I think at some point you're checking an error code to see if the file exists or not. So yeah, that's what's going on here. If we wanted to, for example, just like error out, like fail out if this doesn't work, what we could do is, I mean, this is where we're writing assembly. So think back to the last module, we're writing assembly. We've got this thing sitting in RAX. We can compare it with, let's say, 0. So actually, if we look at man to unlink and we look at the return value on success, 0 is returned. On error, -1 is returned. So we just check if it's successful. Compare RAX 0. We'll say this is the continue label, and we'll say jump if equal to continue, right? Otherwise, maybe what we do is we exit out and we return error code 1, right? Put 60 in for RAX, specify we're going to do an exit, put 1 in for RDI, system call, and now we're not going to continue on if we failed to delete this file. So if we run this, make test, strace./test, we successfully unlinked it, which meant we continued on with the behavior of our program. If we prematurely delete that file and we run it again, we're going to see we do an unlink. This is no longer equal to 0, so our assembly we wrote that branched on if it's 0 or not 0 immediately went off to exit 1. So this is, the previous module is fully at play. Just because we're in like syscall land doesn't mean compares don't exist, right? Compares still exist. This is how you write interesting programs. Just depends what behavior you're looking for in terms of what the heck you write. Okay. Does anyone have any questions about system calls? Yeah, there's a question in the back. So you're talking about this like 66 value? So yeah, so this is system call 2, which is open, which takes flags. Flags is the second argument, so it always goes in RSI. So you always put the flags in RSI for the open system call. Yep. Any more questions? There's a question up here. You good? Yeah. Anyone else have any questions? This is like, what I just wrote here is like the beginning of this module. Technically, we're going down a different path in terms of what system calls we're making, and I'll show off some of those. But this is the basic gist of what this entire next module is going to look like. Yeah. Oh, there's a question on the Twitch. Why is arg1 a const for write but not for read? Const for write but not for read. Oh, right here. So this person is asking right here in this documentation we're looking at, it says character pointer buffer versus const character pointer buffer. That's a good question. I don't think it really matters for our purposes why this pointer should be constant. I mean, either way, you're just passing a value. Like constant is just like a hint. It doesn't actually mean anything. I don't know. I'd have to look into why they decided to classify that as constant versus the other not being constant. I mean, maybe it's because when you read, the contents of this memory is changing. That's the whole point of the read system call, is it lets us read from a file to modify memory. So this is not constant versus, I guess, when you're writing, you're not changing memory. So it's probably that one will change the contents of that memory and one will not. Okay, cool. Awesome. So that is a whole bunch of system calls. Now, coupling, oh, there's a question in the back. Yeah. For example, this call, which is named socket, yeah. We know that the socket function can be configured like here in the socket. How do we know what the values of those integers will be? That's a very good question. So the question is, we've got this socket system call, and it turns out this socket system call, I think it probably starts on like level 2. This is how you build a web server. One of the very first things you do is you create a socket. And a socket is very similar to a file. In fact, it is a file. So the socket thing is in some ways like semantically very similar to the open system call. It's just you're not opening a path name. You're opening like a protocol. So like we're opening and specifying that we want to use TCP IP effectively, rather than saying we want to open flag.txt. And then eventually there's also this bind system call, and you can like bind it to a port. So we like opened it for TCP IP by doing socket, and then we bind this thing to like port 80, and then we're off to the races. So how do you figure out the values to these things? So this is where it's very important to read the man page. So we see that there are 3 integer arguments. So we're not passing in a pointer. There's no pointer to memory or something like that. These are just numbers. Again, these numbers all have meanings in the same way that O read only versus O read write versus O create, those sorts of things. It's the same idea here for this domain, this type, and this protocol. So there's a lot of options with this socket system call. The system call supports a whole bunch of functionality, not just TCP IP, which we'll talk about more in a future module, is one of the primary protocols we're going to use, like for certainly on the internet, and that's what we're going to use to implement our web server. But this system call is also how you could open up Bluetooth capabilities. If you wanted to start listening on Bluetooth and stuff, right, you're going to make a system call or socket system call for that as well. There's a whole bunch of different protocols, and we'll see this talks about some of it. So we see AF_INET is a domain. So the very first thing we're looking at is domain. So let's just temporarily ignore type and protocol. We'll get there. The first one is domain. So we have AF Unix, which we don't need to get into what the heck a Unix socket is, but sometimes they're useful. We have AF_local, which I guess is a synonym for AF_Unix. We have INET, AX25, IPX, INET6. So if you want IPv4 versus IPv6, if you've heard of IPv6, that's what's going on there. We have a whole bunch of options. See that this is where Bluetooth comes in. If you want to get ready to start doing Bluetooth communications, you're going to do AF_Bluetooth. And there's probably more, but this is a whole bunch of them. So the lecture videos talk about all of the system calls that you're going to be making for this module. So it's going to talk about this, and it's going to talk about a whole bunch of the flags. I'm going to tell you right now that what we're doing in building a web server is we're speaking IPv4, as the lecture videos talk about. So we're going to specify this AF_INET thing. Does anyone know how we figure out the value of AF_INET? I'm telling you it's a number. How do we figure out what the value of that number is? Does anyone know? What? I don't think man2IP, or not man2. I don't know which man page that is. It's possible a man page says it. I'm not aware of that. What I would recommend is similar to how we found O create and O read write. We grep through user include. So if I look for AF_INET within user include, this is every time AF_INET is ever mentioned in any header file that exists. Really, we just want #define. And this one's not as easy as O_create or read write. It says that the definition of AF_INET is PF_INET. Well, what the heck is PF_INET? Well, PF_INET is 2. So that's the answer. It's 2. If you want to open up for AF_INET, you're specifying number 2. So that is that one. So 2 is going to go in for domain because I want to do AF_INET. We go to type. What the heck is this type thing? We have options. We can open this thing in sock_stream type, which provides sequenced, reliable two-way connection-based byte streams. An out-of-bound data transmission mechanism may be supported. Or you can do datagrams, which are connectionless, unreliable messages of a fixed maximum length, or you can do whatever the heck seek packet is, or raw, or RDM, or packet. If none of these things mean anything to you, that's totally fine. We'll talk about some of this more in a future module that kind of dives into networking a bit more. You're not expected to understand what the heck any of this stuff means. The answer is we want sock underscore stream. So if you've heard of TCP as a concept, this right here basically is yelling TCP. So we're opening up for IPv4 TCP, and I'm pretty sure the lecture videos talk about how you want all these values. Hopefully I'm not lying about that. And then protocol is it says normally only a single protocol exists to support a particular socket type within a given protocol family, in which case protocol can be specified as 0. I read that sentence and I say, well, maybe I need to specify something else, but it's saying probably I need to specify 0. I'm just going to specify 0 for this thing because that's what it's telling me to specify. So let's go ahead and try this. Actually, we needed that type still also. So we need, what the heck is sock underscore stream? Let's search for that. That is define sock stream as sock stream. Well, that's super useful. Let's just search for sock stream. Well, this person says sock stream is 1. Let's go with it. We can look at strace. Strace will tell us if we're wrong. So if we want to open up this socket, let's just open it up right at the start. There's no reason you can't make a system call whenever the heck you feel like making a system call. We want to do the socket system call, move rex 41. We need this first parameter, move RDI. I believe we said that was 2. Sock stream, it's saying is 1. And then we were thinking, oops, this is our SI. First argument, second argument, third argument, RDX. The man page said 0 is probably going to look good for you. Let's see what happens if we make this, run it, and look at it with strace. Strace knows the names of all these constants and will confirm to us that we didn't mess up. And the kernel will confirm to us we didn't mess up if we get a negative result versus a not a negative result. I guess we didn't see what the return value should be. Let's quickly look at return value. Return value, on success, a file descriptor, exactly the same concept as that open system call that returns a file descriptor. On success, a file descriptor for the new socket is returned. On error, -1 is returned. Okay, so let's go ahead and make test and then strace test. Cool. So it says we made the system call socket. We specified AF underscore INET. We specified sock underscore stream. And we specified IP proto underscore IP. I guess that's what 0 means, is that default thing. So, I mean, this is, yeah, that's what happened there. Let me confirm real quick. Pretty sure. Yeah, see, we talk about all of these things. All of these socket system calls we're going to talk about. And you'll see that in this, this slide right here, this series of slides, is showing you like the first half of the module, how to solve it. So you should be able to solve the first half of this module not too much difficulty, because this is showing you the series of system calls you're going to make and what you're going to pass to it. Or it's very close if it's not that. So as this lecture talks about, we do a socket system call, and then we do this bind system call, then we do a listen system call, then we do an accept system call. Those 4 system calls are all interlinked with each other. We'll see that socket returns a file descriptor, it returns 3. Bind is using that 3, so is listen, and so is accept. They're all referring to the same thing. These 4 system calls are all linked together, and this is how we start a server. These 4 system calls start a TCP server. And then you can just start reading data and writing data, which probably this next lecture video also talks about. And that is our goal. So socket succeeded, and this right here, I'm pretty sure is like level 2 of this series of modules. So some of this is like arbitrary, right? It's like, how the heck do we figure out these numbers? This is how we find these numbers. Does that answer your question of how we find it? Yeah. And I think, does someone else also have a question? Yeah. 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 Yes. Okay. So this right here is system call number 87. And I've already forgotten what the heck we were doing with system call 87. So let's figure out what the heck system call 87 is. This is the unlink system call. So always the return value of a system call goes into RAX. So whatever this is right here, what this semantically means is compare it with whatever this just returned. So whatever unlink just returned is what we're comparing with 0. If we want to know what the heck unlink can return, we do man to unlink, and I search for return, and it tells me about the return value of unlink, which says on success, 0 is returned. On error, -1 is returned. So I'm comparing with, like, semantically, what does this mean, right? This is just a bunch of like x86 instructions, but they have this semantic meaning to them. This instruction right here is saying, did unlink succeed? Like, that's what that means, is did unlink succeed? And then jump equals means it did succeed. So if it did succeed, go off to continue. If this system call for whatever reason did not succeed, we just fall through, and it turns out that this is exit 1. So did that answer your question? Yeah, okay, awesome. Yeah, so it's a lot of like reading documentation. And then if you wanted to know like what the heck does on error, like how are the ways that this thing can fail? Well, it also tells you the errors. So e-access error occurs when write access to the directory containing path name is not allowed for the process's effective UID, user ID, or one of the directories in path name did not allow search permission. Basically, this means I just didn't have permission to access this thing. But I'm trying to unlink something, and I don't have permission to unlink that something. So like, you don't have access to that, like go away. We also have e-busy. This is like probably not gonna happen, but there's ways that a path file name can be like busy, basically. It talks about like NFS. So NFS is like mounting a file system over the network, and because it's over the network, for some reason it could be busy and not available. We don't really care about that. This is just, it does tell us what could happen. E-faults can occur if you give it a bad pointer. So for example, if right here, instead of saying offset path, I give it a null pointer, we're going to see that we get an e-fault. Make test, maybe, how do we comment? I feel like I guess it is pound. Okay. And then strace./test, we'll see that unlink null returned -1 e-fault bad address. So just as I said, if it's a bad address, you get e-fault, and then we didn't get 0, so we go to our exit stuff. If we keep reading, right, we could figure out every single way that unlink can fail, at least according to the documentation. Maybe it can fail in other ways. For all you know, whoever is writing Linux is doing a poor job and the kernel crashes when you do something, and you're not even going to get something. The whole computer will just shut down. I mean, who knows? That could happen. Probably not, but it could. And there's all these other things. For example, your path could be too long. So it's a null terminated thing. If you pass 2,000 characters, it's probably too long. I don't know what the cutoff is. Yeah, there's a question. When you do the system call, you have to clear the other things, like I previously had like RDI and then when you do a system call, it means RDI. Yeah, so that's a good question. So the question is, do I need to clear out other arguments? So for example, maybe this will answer your question. So we're doing the exit system call here, and we know this is going to happen because of what we just set up. What happens if I put move RSI 42, 42, 42 or something. What's going to happen is make test strace./test. What's going to happen is nothing. It works just fine. If you specify a second argument to something that only takes one argument, it's just ignored. Yeah. Anyone else have any questions about making system calls or anything we've done here today? Cool. Okay, so I'm going to jump forward a little bit to a concept that is on one of the later levels, but is something that always trips people up, so I figure I might as well jump forward to it now. Let's go ahead and set up the simple just print hello world program. So we're going to get rid of this. So we have a write system call, and we have we don't care about this path anymore. We're going to write to the screen. So as I talked about on Tuesday, if we make test and then strace./test, we will see, and if I just run it without strace, we will see that hello world just prints on the screen. The reason for that is we have these default file descriptors. It's not really default technically. We have these file descriptors that get inherited from our parent process. So there is a hierarchy to all processes. When we start and we're working over in here, right? Oops. We've got bin bash, right? Right now I'm interacting with bin bash, that is my shell, and I'm able to type stuff like ls into my shell. At some point, I decided to type ./test. The test program runs, bash is still running, and there's a relationship between the test program and the bash program, which is that test is the child of bash, bash is the parent of test. So when we do this, right, there's this hierarchy here. We've got this parent, we've got this child. For example, we could then go on to type ls, and then ls is also a child of bash. Of course, at this point, test has already exited, so maybe you say it leaves the hierarchy or something. I could run bin bash again, right? There's no reason I can't start up bin bash one more time. And I have this fun little ps1 equals $ space to make it so it's minimized. But this is still just bash. But this is no longer the same bash. So we had this bash, now we've also got this bash running. Which means if I start a command from this bash, like ls, we will see ls is now under this, right? So the original bin bash is now the grandparent of ls, right? There's this hierarchy, it's this tree structure of all of my processes. Bash is not special. There's nothing at all special about bash. It is making system calls to influence this process hierarchy. And we've already talked about one just briefly, right? When I strace ./test, we see that this execve system call is being made. There are, for our purposes right now, there are two system calls involved in adding to the process hierarchy. This is one of them. Execve means start up the elf file or whatever at this path. It doesn't have to be an elf file, but start up this program specified by this path. Give it this argv. So this is, right, when you write C and you specify that I'm allowed to have some argv, this is argv0 right here. And then this third one doesn't print very nicely with strace. This is our environment. So it's the same setup as int main in the C world. Except I guess we don't have argc. It figures out how to tell you argc for you. But we have argv and envp being passed as part of this execve system call. If we look in this massive table of things, we will see execve is system call 59. 59 will start up a program specified by this file name with this argv, with this envp, starts the process. However, I said there's two system calls involved here. Right now, the system call that we're going to use, because it's way simpler to think about, there's multiple ways of doing this, but we're going to look at the fork system call. And it's super convenient. Look at fork. It's very easy. There's no arguments to it. It can't be that difficult of a system call. There's no arguments. It takes a little bit of wrapping your head around to understand what the heck's going on with fork. Unfortunately, even though there's no arguments, it's probably going to be the most complicated system call you use throughout this module. Fork splits a process into two processes. At the end of fork, you have two processes. So similar to how exit is weird in influencing this process hierarchy, right? When I type exit, my process just vanishes. It's done. Like there's no code that will be executed after, which is unlike most system calls. Fork is like, in some ways, the opposite of that. Rather than no code will ever execute again after your fork system call, everything after your fork system call will execute twice. It'll execute in one process and another process. So exit means don't execute these instructions ever again. Fork means execute them twice, which sounds wildly uncontrollable, except for the fact that we have this very nice thing called the return value. And the return value is how you deal with this. So it says on success, the PID, the process ID of the child process is returned in the parent and 0 is returned in the child. So everything happens twice because it splits in half, or it doesn't split in half, it splits into two. Oh boy, I just did something to the camera. It splits into two, but in one of these processes, RAX will have a certain value, and in the other process, RAX will be a different value. So that is how you can harness this power, as we will see here in a second. Let's demonstrate that because we talk about this too abstractly for too long, it's going to make no sense. So I am going to make this slightly more correct. I'm going to actually fill in RDI. We didn't have it filled in before. We're specifying 1. 1 means standard out. We'll deal with that again. We talked about it briefly on Tuesday, but this just means write to the terminal for our purposes right now. So if I make test, I run test, hello world pops out. If I strace test, we have write to file descriptor 1, hello world, 14 bytes, then exit. Okay, it really is this simple and this complicated. The fork system call, if I specify RAX is 57, move RAX 57 syscall, I just told you everything after this system call will happen twice. It's not a lie. Watch this. If we make this program, and we run it, if what I'm saying is true, we're going to see the message hello world appear twice, not just once. And look at that, it appears twice. Now this probably, immediately it's not obvious why you would do this, but you could imagine running fork again, right? This is like real weird, right? We run it and then we run it again. Everything happens twice and then everything happens twice again. Everything happens 4 times. I do this, I'm going to see hello world appear 4 times. Hello world, hello world, hello world. And then here we can see $ space hello world. There's a little bit of a synchronization problem here between bash recognizing when the program, it doesn't really matter, it printed again, it's just bash decided to print its prompt before the 4th one decided to. If we ran it again, we'd see it works. There's like, it's non-deterministic who's gonna win this, this print to the screen of this $ thing. Looks like it's very rare, we just got unlucky. And so it splits the process in 2. Now I said, and so did the man page for fork. Return value. If we look at this return value, on success, the process ID of the child process is returned in the parent and 0 is returned in the child. It's a bit of a mouthful, but for our purposes, what we can say is RAX is a different value in both processes. And specifically, one of them is going to have a return value of 0. So let's do that compare thing with 0 again, like we did before. So let's get rid of one of these system calls. Let's move, or let's compare RAX with 0. And what we'll do if jump equal, we'll say this is exit, we'll jump to exit. We'll just exit right away. So what's this going to do? It means now we're only going to see hello world appear once. If I make test and then run test, we see hello world appears only once. If I throw in something like this before, well, if we save this off, let's say move R10 RAX, and now compare R10 with 0, right? So we're just saving the return value of this system call into this register R10. I'm doing that because I'm about to do this. I couldn't not save it off to R10 because otherwise I'm overwriting RAX and we would lose the return value. So I'm momentarily saving it off here. How many times is hello world going to be printed with this setup? I heard 3. Yeah, 3. It's going to print 3 times. Both are going to print this, and then we're going to compare back from this thing, and one of them is going to early exit while the other one prints here again. If we do that, make test 3 hello worlds. You could imagine saying, like, I don't want to print 14 bytes. I only want to print 5 bytes. Actually, we'll do that on this first one. And then what's going to happen? We're going to see hello appear. We're going to see hello appear. And we're going to see hello world appear. And I'm just showing you that, like, you can influence all of these things. This is fully under your control. We got a hello world, and a hello. I think if we do this, it could come in weird orders because all of these things are running simultaneously. Yeah, there's a question.
So, what exactly is the return value of the system?
Of fork?
Yeah.
Yeah. So the return value. So it returns a value twice because there's 2 processes, and each process returns a different thing. So this says the PID of the child process is returned in the parent. So if we think back to this business right here, let's just say this, and then technically what's happening here is test is becoming a child of test. That's kind of what happens because fork splits into 2, but one of them is the parent and one of them is the child. In this process right here, so it says in the parent, we get the PID of the child process. So RAX becomes PID of child. In this one, it says, and 0 is returned in the child. In this one, we get RAX is 0. So the PID of the child, this is literally just like a lot of things in the Linux kernel. It's just a number. It's the sequentially incrementing number. If I how to show this number. If I look in this proc directory, so this proc directory is a very special directory that represents processes as files. I think we previously showed on Tuesday proc self fd, for example. All of these things right here, these are all process IDs. So process ID 1, process ID 117, 120, 127. If I run strace, let's actually just run strace so we can see strace still works here with the fork system call. If we strace this thing, and we have a little bit of an issue, which is I'm going to change standard out this file descriptor 1 so it's no longer printing here so it doesn't interleave with our stuff so that we can just see the system calls and we don't see these hellos showing up. We will see right away we call fork, and strace is telling us that the result of fork is 35909. So this is the perspective of the parent. The parent gets a return value of 35909, and then it does a write of hello, and then it gets this signal. strace also reports signals. It gets this sig child signal. We're not going to go super deep into signals right now, but basically we just got alerted that our child died. The child process died and it sent a signal to the parent process saying, hey, I just died, so that if it wanted to respond to that, it could. There's other ways for it to know that it died. And then we get this write system call and this exit. If we want to see the perspective of both the parent and the child, I don't think there's a very clean way to just see the child. We can do this -F with strace, and -F means follow, which means every time you call fork, also strace that thing. So let's clear this and do strace -F. So, oh boy, let's see here. How do we, I think it like overwrote itself. How do we, maybe fork doesn't show it. I'm going to tell you right now, it's definitely 0. I guess strace, I think it's intertwining with itself in an annoying way. Or actually, I guess the process, the child process didn't call fork. So I guess that's why we don't see fork appear twice. Only the parent called fork technically, and it's just RAX is magically set to 0 in the child. But we can see in different PIDs. So we have PID 36416 versus PID 36415. So 415 is definitely the parent process because it's a smaller number. These process IDs are created sequentially. And also we can see strace says process 36416 attached. It's suddenly attached because it is the child. So the child does this write, the parent does this write. Because we're interleaving things and strace is like trying its best to like handle this simultaneous behavior. It says that like the write resumed in 416 and said 5, and then the write resumed in 415 and did 5. Basically, like these happen simultaneously, but in terms of like actual real time, what happened is this process went off to the kernel, this process went off to the kernel, and then we came back to user space, and then we came back to user space. That's why it does like this resumed thing. Doesn't really matter. And then we exit 0 here in the child, so the child exits, but then the parent does another write, and then the parent, and then let's see here. I guess it says exit resumed, so then the exit actually finished, and then the write resumed, and then we exit. Hopefully it's clear. I mean, this strace is actually not so nice of a way of seeing it because it's all intertwined, but that's what's going on. Does that answer your question? Of RAX being set to a different value? Yeah, okay. Does anyone have any more questions about fork? In some ways, fork is like super simple. In other ways, it's like a lot to wrap your head around of like this thing like splitting in two. It's like a weird mental model. Not seeing any immediate questions. The big thing to know is whenever you're calling fork, you're almost certainly doing a compare RAX after that, or at least saving the value and doing a compare later. But probably you're doing the compare right away. So we do compare RAX. And then this tells us, is this thing the parent or is this thing the child? And if you really care about the process ID, you could save that off to a register or save it off to memory or whatever. But really, the big differentiator is, am I the child or am I the process? And you're going to want to do this. Like every time you do a fork system call, you're going to be comparing, am I the parent or am I the child? And you're going to do a jump to split them so that they're not literally doing the same code. Yeah.
So the only difference between the parent and the child.
Yes. Yeah. Like technically within the kernel, there's now two process things. So if you open a file now in the child, the parent doesn't have that file open. They're now like diverged. But yeah, in terms of registers in memory at that point, everything's the same except for RAX. Cool. Let's see if there was any bonus question. Nope. All right, I think we're probably going to end it there. This is going to be one of the later levels where you need to do this. And the reason you do something like this is so that you can have I'm going to say multi-threaded, but really it's a multi-processed web server. I see there's one question, I think. Yeah. Yes, you can still totally use GDB. If I run make right now, I am in GDB and I can step through things. And if I step here, I can message on the Discord. There's ways to have GDB like switch off into the child or be with the parent because that's where fork gets complicated. But for non-forking behaviors, GDB is very straightforward. Yeah. Cool. And that is all. Thank you all for attending, and good luck.